Welcome to DAR Tutors. Today we're covering R2.1 from the IB Chemistry Higher Level Curriculum, the amount of chemical change. In this video, you will learn to use chemical equations to calculate reacting ratios and determine the amounts of reactants and products. Specifically, we will cover four types of stoichiometry problems: mass-mass, mass-gas volume, gas volume, and concentration problems. First, let's understand how to read and deduce chemical equations. A balanced chemical equation is a powerful tool. It represents a microscopic reaction between colliding particles that we can scale up to the macroscopic world of moles and grams. This equation tells us a few things. Qualitatively, it states that nitrogen dioxide reacts to form dinitrogen tetroxide. Quantitatively, the coefficients, the numbers in front of each molecule, are key. They show the relative number of molecules that react. Here, two molecules of nitrogen dioxide react to produce one molecule of dinitrogen tetroxide. More usefully, the coefficients also represent the mole ratio. So, 2 moles of nitrogen dioxide molecules react to form 1 mole of dinitrogen tetroxide molecules. And from this mole ratio, we can deduce mass relationships. The law of conservation of mass states that the total mass of reactants equals the total mass of products. Let's calculate the molar masses. For NO2, the molar mass is 46.01 g/mol. For N2O4, it's 92.02 g/mol. The equation tells us we have 2 moles of NO2 and 1 mole of N2O4. So, the mass of reactants is 2 times 46.01 grams, which is 92.02 grams. The mass of product is 1 times 92.02 grams, which is also 92.02 grams. Mass is conserved. For gases, Avogadro's law provides another quantitative link. Mole ratios are equivalent to volume ratios at the same temperature and pressure. So 2dm3 of nitrogen dioxide will react to form 1dm3 of dinitrogen tetroxide. This means that for the same conditions, the volume of gaseous reactants and products also follows the 2-to-1 ratio. Now let's look at how to balance a chemical equation when you're given the reactants and products in a word equation. We need to ensure that the number of atoms of each element on the reactant side is equal to the number of atoms of the same element on the product side. Let's use an example. Consider the reaction between ammonia and nitrogen monoxide to produce nitrogen and water. First, we write the correct chemical formulas for all substances. Next, we balance the elements one by one. It's often easiest to start with elements other than hydrogen or oxygen, as they frequently appear in multiple compounds. Here, let's balance hydrogen first. On the left, we have 3 hydrogen atoms in NH3 On the right, we have 2 in Mar2. The least common multiple is 6. We place a coefficient of 2 in front of an $3 and 3 in front of a $2. This gives us 6 hydrogens on both sides. Now, let's balance oxygen. On the right, we have 3 oxygen atoms in 3H+2. On the left, we have 1 oxygen atom in NO. To balance oxygen, we need to place a 3 in front of NO. So now the equation reads 2 in H+3 plus 3. NO yields N2 plus 3H2. Finally, we balance nitrogen. On the left, we have a total of 5 nitrogen atoms. 2 from 2 in H3 and 3 from 3 NO. On the right, we have 2 nitrogen atoms in a $2. This gives us 2 ma H+3 plus 3. Yields 5/2 plus 3 yap a $2. To avoid fractional coefficients, we multiply the entire equation by 2. This gives us 4H3 plus 6 O yields 5 or $2 plus 6 2 Multiplying the entire equation by 2 gives the final balanced equation. 4 $3 plus 6 no yields. 5 $2 plus 6 is $2. Finally, we add state symbols. For instance, for standard conditions, it would be 4H3 G plus 6 OG, I'd arrow 5 and 2 G, 6 and 2 tool so. This process of writing correct formulas and then balancing the number of atoms is fundamental to all stoichiometry problems. Now let's apply these principles to a specific type of stoichiometry problem: mass-mass problems. In these problems, you're given the mass of one substance in a reaction and asked to find the mass of another. The key is to convert everything to moles first. Let's outline the steps. There are 3 core steps. First, convert the given mass to moles. Second, use the balanced chemical equation to find the mole ratio and calculate the moles of the substance you need to find. Third, convert those moles back into a mass. Let's work through an example. Let's determine the mass of mercury produced from the decomposition of 0.00125 kilograms of mercury 2 oxide. The balanced equation is 2Hg yields 2Hg plus O2. Step 1. Convert kilograms to grams. 0.01225 kilograms is 1.25 grams. Then calculate the molar mass of mercury 2 oxide, which is 216.59 grams per mole. Now we find the moles of HgO by dividing the mass by the molar mass. 1.25 divided by 216.59 equals 0.0577 moles of Hg. Step 2. Use the mole ratio. From the equation, 2 moles of HgO decompose to form 2 moles of Hg. This is a 1-to-1 ratio. Therefore, our 0.00577 moles of HgO will produce 0.00577 moles of mercury. Step 3. Convert moles of mercury to mass. The molar mass of mercury is 259 grams per mole. Multiplying the moles by the molar mass, 0.00577 moles times 259 grams per mole gives us 1.16 grams of mercury. Let's try another example. When 4,900 grams of potassium chlorate are heated, it decomposes to form potassium chloride and oxygen. We need to find the mass of oxygen produced. Step 1. Molar mass of KClO3 is 122.55 grams per mole. Moles of KClO3 is 4,900 grams divided by 122.55 grams per mole, which is 0.400 moles. Step 2. The mole ratio of KClO3 to O2 is 2:3. So 0.400 moles of KClO3 will produce 0.400 times 3 halves, which equals 0.600 moles of oxygen. Step 3. The molar mass of O2 is 3,200 grams per mole. Mass of O2 is 0.600 moles times 3,200 grams per mole, which is 19.2 grams. Notice we report the final answer to 3 significant figures, matching the precision of the starting data. Next, let's tackle mass-gas-volume stoichiometry problems, a variant of mass-mass problems. Here, you are given a mass and need to find the volume of a gas produced or consumed at standard temperature and pressure, or STP. We use the same 3-step process. The first 2 steps are identical. Convert mass to moles, then use the mole ratio. The only difference is the 3rd step. Convert moles of gas to a volume using the molar gas volume constant at STP. Let's find the volume of hydrogen gas produced from the reaction between 1.64 grams of aluminum and hydrochloric acid at STP. The equation is 2AeL plus 6HCl, yields 2AlCl3 plus 3H2. Step 1. Convert aluminum mass to moles. Molar mass of Al is 26.98 grams per mole. Moles of Al is 1.64 divided by 26.98, which is 0.0608 moles. Step 2. Use the mole ratio. The equation shows a 2:3 ratio between aluminum and hydrogen gas. So, moles of H2 equals moles of Al times 3/2. This is 0.0608 times 1.5, which is 0.0912 moles of H2. Step 3. Convert moles of hydrogen gas to volume. At STP, 1 mole of any gas occupies 22.7 cubic decimeters. Volume of H2 equals 0.0912 moles times 22.7 dm3 per mole, which is 2.07 dm3. Let's work through another problem. What volume of carbon dioxide is produced from the complete combustion of 17.117 grams of sucrose at STP? The molar mass of sucrose is 342.34 grams per mole. Step 1. Moles of sucrose equals 17.117 grams divided by 342.34 grams per mole, which is 0.0500 moles. Step 2. The mole ratio between sucrose and CO2 is 1 to 12, so moles of CO2 equals 0.0500 times 12, which is 0.600 moles. Step 3. Volume of CO2 is 0.600 moles times 22.7 dm3 per mole, which is 13.6 dm3. Now let's move to concentration stoichiometry problems. These are common in titration experiments. In these problems, you're given the volume and concentration of one solution and asked to find a property of another. Again, we follow a three-step process involving moles. The steps are: first, calculate moles of the known substance using the concentration formula. Moles equals concentration times volume. Second, use the mole ratio to find the moles of the unknown. Third, use the moles of the unknown to find its concentration, volume, or even mass. Let's work through an example. Find the volume of a 0.610 molar sodium hydroxide solution needed to neutralize 0.0200 dm3 of a 0.245 molar sulfuric acid solution. The balanced equation is 2NaOH plus H2SO4 yields Na2SO4 plus 2H2. Step 1. Calculate the moles of sulfuric acid. Moles equals concentration times volume, which is 0.245 molar times 0.0200 dim3. This gives us 4.90 times 10 to the power of minus 3 moles of H2SO4. Step 2. Determine the moles of sodium hydroxide. The mole ratio from the equation is 1 mole of H2SO4 reacts with 2 moles of NaOH. So, moles of NaOH is 2 times 4.90 times 10 to the power of minus 3, which is 9.80 times 10 to the power of minus 3 moles. Step 3. Calculate the volume of sodium hydroxide. We rearrange the formula C equals N over V to V equals N over C. Volume of NaOH is 9.80 times 10 to the power of minus 3 moles divided by 0.61 moles per dm3, which equals 0.0161 dm3. Let's try another problem. What is the maximum mass of anhydrous zinc sulfate crystals that can be formed when 100 cc3 of 2.0 molar sulfuric acid is reacted with excess metallic zinc? First, we need the balanced equation. N plus H2SO4 yields ZnSO4 plus H2. Step 1. Convert 100 PgE3 to dm3 by dividing by 1000. This is 0.1000 dm3. Moles of H2SO4 is 2.0 m times 0.1000 dm3, which is 0.200 moles. Step 2. Since we have excess zinc, sulfuric acid is the limiting reactant. The mole ratio from the equation is 1 to 1. So, the maximum moles of zinc sulfate that can be produced is 0.200 moles. Step 3. Calculate the mass of zinc sulfate. The molar mass of ZnSO4 is 161.47 grams per mole. Mass equals 0.200 moles times 161.47 grams per mole, which is 32.3 grams. Finally, let's look at gas volume problems. These are the most straightforward. Avogadro's law simplifies these problems. Because equal volumes of gases at the same temperature and pressure contain the same number of molecules, the coefficients in a balanced chemical equation represent not only the mole ratio, but also the volume ratio. So to solve these, you only need one step. Convert the given volume to the required volume using the mole ratio directly. You do not need to convert to moles because the mole ratio is the volume ratio. Let's see how this works. Example. Determine the volume of oxygen gas that reacts with 2.75 dm3 of sulfur dioxide gas to form sulfur trioxide gas. The balanced equation is 2SO2 plus O2 yields 2SO3. From the equation, the mole ratio of sulfur dioxide to oxygen is 2 to 1. This means the volume ratio is also 2 to 1. So the volume of oxygen is half the volume of sulfur dioxide. We calculate 2.75 dm3 times 1/2, which equals 1.38 dm3s. It's that simple. Let's try one more. When nitrogen and hydrogen react to produce ammonia, what volume of hydrogen is used if 12.5 dm3 of nitrogen is consumed, and how much ammonia is produced? We assume standard conditions. First, we need the balanced equation. 2 plus 3H2 yields 2NH3. The mole ratios are 1 to 3 to 2, so the volume ratios are also 1 to 3 to 2. To find the volume of hydrogen, we look at the N2H2 ratio of 1:3. Volume H2 is 12.5 dm3 times 3, which is 37.5 dm3. To find the volume of ammonia, we use the N2.NH3 ratio of 1/2. Volume NH3 is 12.5 dm3 times 2, which is 25.0 dm3. Now let's explore the concepts of theoretical, experimental, and percentage yield, which are crucial for understanding the practical outcomes of reactions. We've been calculating the theoretical yield, which is the maximum amount of product that could be formed from a chemical reaction, calculated from the stoichiometry. In reality, we never achieve 1/2 of the theoretical yield. This is where experimental yield comes in. It's the actual mass of the product obtained when the reaction is carried out in the lab. The reasons for the discrepancy are numerous. The reaction might not go to completion. There could be side reactions producing unwanted products, or we might lose some product during purification. The experimental yield is always less than or equal to the theoretical yield. So how can we quantify the efficiency of a reaction? We use percentage yield. This is the experimental yield divided by the theoretical yield, multiplied by 100 to express it as a percentage. It tells us what proportion of the maximum possible product we actually managed to get. Let's work through an example to illustrate this. Imagine we are synthesizing aspirin in the lab. We start with 5 grams of salicylic acid and react it with acetic anhydride. According to our stoichiometric calculation, the theoretical yield of aspirin is 6.53 grams. However, after we carry out the reaction and purify our product, we find that we only have 4.85 grams of aspirin. This is our experimental yield. To find the percentage yield, we plug these values into our formula. 4.85 grams divided by 6.53 grams, all times 100%, gives us a percentage yield of 74.3%. An extension of yield is atom economy, a concept important in the principles of green chemistry. Atom economy is a measure of the efficiency of a chemical reaction. It specifically looks at how much of the starting material's atoms end up in the desired product, rather than being wasted in byproducts. The formula is the sum of the molar masses of the atoms in the desired products, divided by the sum of the molar masses of the atoms in all products, including byproducts, times 100. A high atom economy is desirable because it means less waste is generated, making the process more sustainable. Let's compare two common methods for producing ethanol to see which is more atom economic. Method 1 is the fermentation of glucose. The equation is C6H12O6 yields 2C2H5OH plus 2CO2. The desired product is ethanol. Its molar mass is 46.07 g/mol. The total molar mass of all products, ethanol and carbon dioxide, is 134.14 g/mol. The atom economy is 92.1 phen divided by 134.16 times 100, which is approximately 68.7%. So 68.7 tt of the original glucose atoms ended up in the ethanol. Now let's look at method 2, the catalytic hydration of ethene. The equation is C2H4 plus H2O yields C2H5OH. Here, ethanol is the only product. The molar mass of the desired product is 46.07 g/mol, and the total molar mass of all products is also 46.07 g/mol. The atom economy is 46.07 divided by 46.07 times 100, which is 102. This comparison highlights a key principle. In terms of atom economy, the hydration of ethene is a more efficient and sustainable process than the fermentation of glucose because it produces no waste byproducts. A final topic of stoichiometry is limiting and excess reactants. In a chemical reaction, we often don't mix reactants in their exact stoichiometric ratio. When this happens, one reactant will be completely used up before the others. This reactant is called the limiting reactant. The limiting reactant dictates the maximum amount of product that can be formed. In other words, the theoretical yield. The other reactant, which is left over, is the excess reactant. Think of it like making cheese sandwiches. If you have 10 slices of bread but only 4 slices of cheese, the cheese is your limiting ingredient. You can only make 4 sandwiches, even though you have enough bread for 10. The bread is in excess. To identify the limiting reactant in a chemistry problem, you must calculate the amount of product that can be formed from each reactant individually, assuming the other is in excess. Let's use an example. Suppose we have 25.0 grams of hydrogen gas reacting with 25.0 grams of oxygen gas to form water. First, calculate the moles of each reactant. Moles of hydrogen is 25.0 divided by 2.02, which is 12.4 moles. Moles of oxygen is 25.0 divided by 32 Hg, which is 0.781 moles. Next, calculate the theoretical yield of water from each reactant. The ratio H2 to H2O is 2 to 2 or 1 to 1. So, 12.4 moles of H2 can make 12.4 moles of H2. For oxygen, the ratio is 1O2 to 2 H2O. So 0.781 moles of O2 can make twice that, 1.56 moles of H2O. Comparing the two, oxygen can only produce 1.56 moles of water, while hydrogen could produce 12.4 moles. The smaller amount is the limiting amount. Therefore, oxygen is the limiting reactant. To finish, let's work through a more complex, multi-step problem that combines several of these concepts. This is the kind of higher-level analytical thinking you'll need for the IB chemistry exams. The problem involves determining the percentage of ozone in a gaseous mixture through a series of titrations. The process involves 3 steps. First, ozone in a gaseous mixture reacts with iodide ions. Second, the iodine produced in the first step is reacted with thiosulfate ions in a titration. Third, we use the results of the titration to find the amount of ozone and its percentage in the original mixture. We passed 500 cm3 of the oxygen-ozone mixture through potassium iodide. The iodine produced was titrated with 0.100 T sodium thiosulfate, requiring 1500 cm3 to reach the endpoint. First, we calculate the amount of thiosulfate used in moles. Remember to convert volume to dm3 by dividing by 1000. Moles of S2O32 equals 0.01500 dm3 times 0.100 m, which is 1 µ times 10 to the power of minus 3 moles. Second, we use the stoichiometry of the second reaction to find the moles of iodine. The mole ratio of iodine to thiosulfate is 1 to 2. So the moles of I2 is half the moles of S2O32, which is 7.50 times 10 to the power of minus 4 moles. Third, we use the stoichiometry of the first reaction to find the moles of ozone. The mole ratio of ozone to iodine is 1 to 1. Therefore, the moles of O3 in the original mixture is also 7.50 times 10 to the power of minus 4 moles. Fourth, we convert the moles of ozone to a volume. At STP, the molar volume is 22.7 dm3 each mole. So the volume of O3 is 7.50 times 10 to the power of minus 4 moles times 22.7 dm3 each mole, which is 0.0170 dm3. Converting to cm3 gives 17.0 cm3. Finally, we calculate the percentage of ozone. It's the volume of ozone, 17.0 cm3, divided by the total volume of the mixture, 500 cm3, multiplied by 100%. This gives us 3.40% ozone by volume. To solidify your understanding of stoichiometry, we will now go through 5 IB-style practice questions with fully worked solutions. Question 1 asks about a mass-mass calculation. First, write and balance the equation. Next, calculate the moles of HCl. Then, use the mole ratio from the equation, 1 mole of KCO3 to 2 moles of HCl, to find the moles of KCO3. Finally, convert moles of KCO3 to mass using its molar mass. The answer is 2.50 grams of calcium carbonate. Question 2 is a gas volume problem, using the molar gas volume. First, balance the combustion equation. Since all reactants and products are gases, we can use the volume ratio directly. The equation shows a 1:2 ratio between ethene and carbon dioxide. Therefore, the volume of CO2 is twice the volume of C2H4, which is 100 centimeters cubed. Question 3 involves percentage yield. First, we find the theoretical yield of ethyl ethanoate. We convert the given mass of ethanol, 23.0 g, to moles. The mole ratio from the balanced equation is 1:1. So we form 0.500 moles of ethyl ethanoate. We convert this to a theoretical mass of 44.05 g. The percentage yield is the experimental yield divided by the theoretical yield times 100, which gives 68.1%. Question 4 asks for the limiting reactant. We need to find out which reactant produces less product. We convert both magnesium and oxygen to moles. Moles of Mg is 0.411 mole, and moles of O2 is 0.313 mole. Then we calculate the moles of product MgO from each. From 0.411 mole Mg, we get 0.411 mole MgO. But from 0.31 to 3 mole O2, which has a 1:2 mole ratio, we could make 0.626 mole MgO. Since magnesium produces the smaller amount of product, magnesium is the limiting reactant. Finally, question 5 tests your knowledge of atom economy. The question provides a lot of context, but the core calculation is for the electrolysis step. Al2O3 breaking down into Al and O2. We apply the formula for atom economy. The desired product is aluminum, so we need the molar mass of 2 moles of Al. The total products are 2 moles of Al plus 1.5 moles of O2. Plugging in the values, we get 54.0 grams for the desired product and 102.0 grams for the total products. The atom economy is 53.96 divided by 101.96, multiplied by 100%, which is 52.9%. This means that in this step, almost half of the mass ends up as oxygen gas, a byproduct. We have now covered the fundamental principles and calculations of stoichiometry that are essential for the IB Chemistry higher level curriculum. You should now be able to interpret chemical equations, perform calculations involving mass, volume, and concentration, and confidently solve problems related to limiting reactants, percentage yield, and atom economy. Remember, practice is key to mastery. Work through many different types of problems to become proficient. For expert, personalized tuition in IB A-Level and IGCSE chemistry and other subjects, please contact DAR Tutors. Our experienced tutors can provide the support you need to achieve your academic goals.